Welcome back to the Deep Dive. We take complex science and, well, make sense of it for you. Today we're going right down to the basics, the atom. Okay, let's unpack this. We want to get really fluent in atomic language. What are atoms actually made of? How do we measure them? And crucially, how do their properties repeat across the periodic table? That's our mission today.
Exactly. And, before we jump into anything complicated, we have to know the players. An atom boils down to just three fundamental bits: protons, neutrons, and electrons. So you've got the protons and neutrons clustered together in the nucleus. They're the heavy hitters, relatively speaking, mass of about 1 each. Protons have that positive charge, +1. Neutrons, well, they're neutral, 0 charge.
And the electrons.
The electrons. They're whizzing around outside the nucleus in orbitals, tiny mass, like 11/18/40th of a proton, basically negligible. But they're charged, that -1 charge, that dictates pretty much all of chemistry.
Right. And we have a neat shorthand for this, don't we? That's standard notation. If you see, say, $73 for lithium, the little number at the bottom, Z, the atomic number, that's 3, that tells you it has to be lithium because it has 3 protons. That number defines the element.
Spot on. It's the proton count.
And the top number, A, the mass number, is 7 here. That's the total protons and neutrons together in that specific atom's nucleus.
Yeah.
So calculating neutrons is easy, right? Just A minus Z. For this lithium, 7 minus 3 is 4 neutrons. It's like its atomic ID card.
Precisely. And that difference in neutron count leads us straight into isotopes.
Oh, yes, isotope.
Atoms of the same element, so they have the same number of protons, meaning they behave almost identically in chemical reactions because their electrons are arranged the same way, but they have different numbers of neutrons.
So same chemistry, different mass.
You got different mass, which can slightly change some physical properties, but chemically they're siblings.
Okay, we've established mass is important, but these things are incredibly tiny. How do we even talk about their mass in a useful way? We need some kind of standard, right?
Absolutely. We need a universal benchmark. And the one we've all agreed on is based on carbon-12. We define our unit as exactly 112th the mass of a single carbon-12 atom.
Okay, so everything's relative to that carbon-12 slice.
Exactly. And using that standard lets us define 3 really important relative mass terms. First, relative isotopic mass. That's simply the mass of one specific atom of one isotope compared to that standard.
Makes sense.
Second, relative molecular mass, usually written as million-dollar dollars. That's the average mass of a whole molecule, again, relative to 112th of carbon-12.
Okay.
But the big one, the one you see on the periodic table, is the relative atomic mass, or RAM. This is the weighted average mass of one atom of an element, taking into account how abundant each of its natural isotopes is.
Right, so that number for magnesium, 24.3, isn't just for one type of magnesium atom. It's an average of all the naturally